In this video, we're going to start analyzing the maximum signal handling capability of receiver chains by building a model of a nonlinear system. This is an interesting departure from the rest of the course, where everything we analyzed was very linear. Though this video has the word amplifier in the title, the techniques we're going to learn apply to other nonlinear devices, like power detectors, too. This page shows a schematic of an amplifier with an input voltage and an output voltage. The schematic also reminds us that we can think of the amplifier as having an input power and an output power, which ties back to the concepts of power gain that we talked about earlier. You can calculate the amplifier's input and output power by squaring the voltage and dividing by the impedance, which is usually Z0 in an RF system. The slide also shows an equation and a graph that indicate the relation between Vout and Vin, which is called the transfer characteristic. The transfer characteristic is pretty simple for an ideal amplifier. It just makes its output linearly bigger than the input. So we see that the equation multiplies the input by the voltage gain A1, and the graph is just a line with a slope of A1. Unfortunately, real amplifiers aren't perfectly linear. At minimum, they're limited by their power supplies, and there could be other nonlinearities in the amplifier too. That means we need to represent amplifiers with Taylor series that capture their nonlinear behavior. We can make some guesses about the value of the Taylor coefficients for normal amplifiers. Amplifier curves are usually odd or close to it because they try so hard to be linear near the origin. That means the A2 coefficient is usually small. Also, amplifiers are usually compressive because they clip on the power supply. So the A3 coefficient is usually negative, which starts canceling out the straight line from A1 at high Vin values. Finally, when we're working with transfer functions, it's easy to forget that the inputs to an amplifier are usually time varying. In this last set of equations, I've assumed that our Vin is a sinusoid, which is normal for RF systems, to remind us that Vout is a time varying quantity. In the next few videos, we're going to see that squaring and cubing sinusoids has surprising effects on our output spectrum. So in summary, we represent nonlinear amplifiers using Taylor series. The second order coefficient of Taylor series is small because amplifiers usually have odd transfer characteristics. And the third order coefficient of Taylor series is usually negative because amplifiers are compressive at large signal levels.